Okay, so welcome back. Now we understand what the feasibility of learning means. So we broke it down into two questions, and now we are trying to understand the Hofding's bound. In fact, we're trying to interpret the Hofding's bound in order to make it fall in line with the question that we asked earlier, whether learning is feasible or not, right? So we know that the larger part of the feasibility thing is that there is a relationship between E in and E out. And luckily, we have this Hofding's bound that gives us that relationship, right? So here, probability of something bad happening, that means the difference between E in and E out is more than my tolerance, is bounded by this term here. And then there's the inverse, like probability of some good thing happening is obviously 1 minus that. Okay. So now I'm going to state a theorem here that will further add to our understanding of the relationship between E in and E out. Okay, and I'll try to make things concise by introducing this delta. So now delta stands for 2 and h. And by the way, I think I forgot to mention, now we had m here earlier, if you remember the derivation that we did. That m has been replaced by the cardinality of h because this is more specific to the way we have defined our learning problem, right? So essentially, instead of m, we will be writing the cardinality of h, which is the number of hypotheses here, right? Okay, so 2h e to the minus 2 epsilon square n, right? So let's say that that's delta. Now what this theorem states, and let me write it down, is that with probability, and I'm restating essentially this statement. So keep an eye on that. It's essentially restating that, and we'll also prove it, right? So with probability, at least 1 minus delta, because this here is delta, right? This term here is delta. So with probability at least 1 minus delta, we can say that E out of G, which is the out of sample error on our final hypothesis G, is less than equal to E in of G plus the square root of 1 over 2n log 2 times the cardinality of H over my delta. This is the theorem. Now, let's prove it using the Hofding's bound, of course, right? So let me write the proof here. Okay. Now, we know that, like from the Hofding's inequality, that the probability of E in for G minus E out for G less than equal to my tolerance, right, is greater than equal to 1 minus delta, where delta I've just defined, right? In other words, like with probability at least 1 minus delta, right? In other words, I can write that with probability at least, and this at least is coming from this like greater than equal to sign, with probability at least 1 minus delta, right? We can say that the difference, the absolute difference in E in of G minus E out of G is less than equal to my epsilon, which again, a reminder, epsilon is nothing but the tolerance level that I will decide for my learning problem. In other words, we can rewrite this. This implies, I can say that E out G is less than equal to E in of G plus my tolerance. Now, from my definition of delta, and let me write it down here, we define delta as something like this, 2h e to the minus 2 epsilon square n, right? So from my definition of delta itself, and because I've defined this delta as a collective term for my bound, I can derive my tolerance using this, right? So with some algebraic manipulation here, right, I can get my epsilon equal to the square root, and then you can try it yourself. It's simply like moving terms here and there. That's all we're doing here. And then you can get log 2 times h, sorry, h is the cardinality of h over delta, right? Which means essentially we have a more sort of tangible, I would say, relationship between E out and E in. And why are we doing that? I'm coming to that in a second. Let me just like write it down. This plus whatever epsilon we got here, this value will come here. And so we are going to have square root of 1 over 2n log 2h over delta. This term is known as the error bar. Okay, so now we have, as I said, an exact sort of relationship between, I wouldn't say an exact, but sort of a better relationship between E out and E in. And the reason for why we are doing that is for the feasibility of learning. And for learning to be feasible, there has to be a way of reaching out to the universe of the problem that we are solving. So there has to be a way of reaching out from the sample to the actual data, right? So that's why we derived this. So we can say that there is a way of reaching out to the data. So there is a way that E in can reach out to the data, except that it has this like error term there that will always exist. And if we look at the variables here, the n and the h, these are definitely going to impact on how much can we reach outside the data, right? Because you can see that this E out is at least less than or equal to this thing, right? So this term matters, this error bar matters. Okay, so how much does that matter? Let's try to answer that question. Okay, so with the theorem in the previous slide, we have established that E in reaches out to E out, but with an added error bar, right? So we have this error bar that's added, right? And so that's why the statement here when h is small, because you can see that this h and n both impact my reaching out to E out. And that is the basic question that I'm trying to actually answer in a learning problem. How much can I, like from my data, how much can I infer about outside the data, right? So from the derived equation, which is also known as the generalization bound many times, this is also known as the generalization bound, right? From this derived equation, we can infer a lot of things. So let's look at this first. If like, let's say n, which was my sample size, right? This was my sample, and this was the cardinality of my hypotheses, right? So what happens if my n is really, really big, it's huge, and it's bigger than log of h, right? Because essentially this is the log, this is a constant, 2 is a constant. So I'm like, I have more care about like this thing here, 2 is a constant. So if n is like really big and way, way bigger than this, then this will diminish this term, right? This will become really small. The error bar will become really small. And so we can say that E out of G comes really, really close to E in of G. So somewhat we are answering that first question of the feasibility of learning, right? And yeah, we can definitely do that. Now, the second question, if you remember, was what happens? Okay, I understand that E out is really close to E in, and this is a good thing because what we have is essentially E in. But if based on like N and H, we can bring it down, right? This error bar, then I can ensure that E out is going to be close to E in. But what exactly is this E out? Is my E out of G, which is the error in the actual data, what value does it have? Right? So that is the question that still remains. Because like if you remember the learning problem and the way we defined it, it was basically that we were trying to answer the question, what happens to my E out, right? I was trying to have the E out as like really small and not just E in. Because E in was talking about the data that I have, but E out is answering the larger learning problem. Okay, so let's try and understand that in terms of this trade-off. A bit of it you've seen before, but let's talk through this. So if I plot in general the overall error in my learning problem and the number of hypotheses we have, and now we've looked at that this is somehow impacting the question that I'm trying to answer about my feasibility of learning. And so in a way, it's impacting the question of whether E out is going to be small enough or not, right? So let's try to understand that. Let's look at this blue curve, the in sample error, or let me write it. This is essentially E in of G. That's the blue curve. So what's happening is, as my H is increasing, obviously this is where it is increasing, and this is how the error is increasing. So as my hypothesis set, the cardinality of that is increasing, it is more likely that we will find a G, right, a final hypothesis G, that has lower in sample error, right? Which is why the overall behavior of the in sample error is this blue curve, that it keeps going down as I have more and more to select from, right? Now, looking at the error bar, right, if we go back and check our error bar equation, which was this here, right? If I look at that, what's happening if I'm getting more and more flexibility to choose from, I'm paying a price because my error bar, the value of my error bar is going up, right? And as I am increasing my edge, I'm paying the price because I have more choices, right? So as we said earlier, choices come with a price. Okay, to make things simpler, what we've done here is, this is the error bar, of course, was here. Let us assume that it is some omega. Let's actually represent it using omega, which is a function of my hypothesis. We can do that, right? This is nothing but some function of some variables, which is h and n. If you think about n, it's representing my data, so it's mostly fixed. It's typically fixed, right? So essentially, my omega depends on my h. And as I said, think of this like entire error bar as a penalty for complexity. So let me write it down, model, and it's actually written here. Model complexity, also it's a penalty that you pay for increasing the complexity, right? So that error bar has that's also a component of learning of error, right? And what's happening is that this model complexity is increasing as I'm increasing h, because like omega is a function of h, and you can see that if h increases, this error bar goes up, right? So these are the two components on the right hand side of this equation, right? E in reaches out to E out. We talked about E in, we talked about the model complexity in terms of the error bar, and you can easily tell that there is a trade-off, right? Like this thing is increasing as we are increasing the hypotheses. The error, the E in is going down as we are increasing the hypotheses number, right? Now, if we combine both of them, that is what the out of sample error is, or this is what the E of out is. Right, and you can tell just by looking at this equation, this is what we are trying to get. And we are trying to really, get a very small E out, because that's the whole point of my learning, right? I need to reach out to the data and have the error as small as possible. Okay, so how will I get the error as small as possible? Because I mean, there isn't a way that like I'm going to decide, okay, I want this much error and then I'm going to fix it. That's not going to happen, because we have derived this relationship between the out of sample error that kind of depends on the in sample and the model complexity, right? And now we know what this model complexity means, and we know what in sample error means. And based on that, we plotted the error and the number of hypotheses in my hypothesis set and came up with this graph. Now, if we add this blue and this red, we get this like purple thing, which is out of sample error. And this is the curve that will result out of that. Now, the good news here is that there is this optimal hypothesis set that will minimize my overall error, right? Basically, the point I'm trying to make is that basically there's no way out getting out of these two errors. They will be there, but we have to work our way through so that we can get something that's minimum, because that's what my goal is, right? Essentially, this optimal hypothesis set, which like minimizes both the sum of the errors like the E in and the model complexity, it accomplishes this optimal value. It accomplishes the trade-off between E in and model complexity, which meant not paying too much price. So I've reached at a point where E in will be relatively small. Of course, it's not here. But then if it was here, if I chose this hypothesis, I'm really paying a lot of price. And then the total error is larger than what we could have achieved. So my goal is to essentially get this optimal hypothesis set, where I'm not paying too much price and still managing to get a decent E of n. Okay, so this is a fundamental trade-off in machine learning. In fact, as machine learning practitioners, you will see that most of your time is spent in like achieving this or arriving at this point, right? So this is a fundamental trade-off and it's always there. And we really care about E out. We know that, right? The learning problem is all about reaching to E out and having it as small as possible. And E out is connected to E in and model complexity through this trade-off and through this equation. Okay, so summarizing everything and putting things in perspective, there is like, so what are the questions that we need to address? Now we have established that my E in of G is close enough to E out of G, right? Um, okay, that's all fine. But remember 2 slides earlier, we talked about E out of G. We should know about that because if you remember, the learning problem was that my G should be as close to my learning target function as possible. So this is all by itself not answering this question. Of course, we are able to reach out to the universe of data from our sample, right? So we are reaching from sample to universe, of course, through this equation, but we are still deficient in terms of answering this question. So let's try to answer this question. Or if we want to like further simplify this, because now we are talking in terms of error. So let's like simplify this. Our goal in learning is to get E out of G as small as possible. So basically making it 0. So are we able to do that or not? That's the question that we need to answer. And to answer that question, we have a 2-step approach to learning. Okay, what is that 2-step approach to learning? So there are 2 components of learning always. The first step is that we need to ensure that my E out of G is really close to E in of G. And we've seen that before, of course, right? So we have to ensure this at all times. Now, I don't know anything about E out of G, but this is a valid question. I mean, learning is all about getting a small E out. But how do we do that? We don't know anything about like E out directly. But it seems there is an indirect way of ensuring that. So that's why we have this 2-step approach. The second is we should get E in as small as possible. And of course, keeping into account the trade-off and everything, but get E in as close to 0 as possible. So now if we put together these 2 steps, right, this in turn implies, and let me write it, these 2 steps together, this implies that E out of G is going to be indeed equal to 0 if we have ensured these 2 things. Now we know how to ensure this with the equation that we have earlier, right? The error bar equation, the theorem essentially, right? And then the second step is to have E in as small as possible, essentially choosing a G such that it's really minimizing or coming close to 0 because that's what we like, right? We want the error to be as small as possible. And if we put these 2 together, this together implies E out of G. So we have an indirect approach to getting E out of G equals 0, which in turn implies we have an indirect approach to validating that G comes really close to F. This is obviously not a direct approach, but it seems that is enough, right? So we have a 2-step approach. Whenever we are solving any machine learning problem, we have to ensure these 2 steps. Okay, so that's it in this video. I'll see you in the next video in which we'll take this further ahead and see and go from there.